Hello everyone, I'm using a different function than I did in the previous videos from day 7, well earlier on in day 17. Here we have f of x equals x squared instead of x squared plus 1. And I decided to start at -1 instead of 1, and I decided to end at 2. I just want to give you another example. And I said we're going to squeeze 3 rectangles in there. So it'll be necessary for us to figure out how thick those rectangles can be. So let's see, our delta x, which is b minus a over n, should equal, let's see, so the furthest right is 2 minus -1. And we're going to take this distance from -1 to 2, which is a distance of 3, and divide it by 3. So that tells us that the thickness of each one of our rectangles should be 1. And notice I did exactly that. -1 plus 1 is 0, plus 1 is 1, plus 1 is 2. All right. So what I've done here is I have shaded in blue the exact area under the curve, which is what I like. But a long time ago, they didn't have an easy way to find that, so they used rectangles. They actually used, they could have used trapezoid or any other geometric figure, but we're going to stick with rectangles. Okay, so I decided to do the left endpoints, and for these left endpoints, notice between -1 and 0, -1 is on the left, so that marked out the first height. Between 0 and 1, 0 is on the left. And then between 1 and 2, the 1 is on the left, right? So if I add these 3 rectangles, then I'm going to argue that the sum of those rectangles is the approximate blue area, right? The approximation of the exact area under the curve. So let me show you the work down here. Notice what I'm suggesting. Add up the area of rectangles, height times the base. Again, f of x is your height, your delta x is your base. So I did the work here. Notice my first height was determined at -1, so f of -1 times a base of 1. The second height was determined at 0, so f of 0 times 1. The third height was determined at 1, which is why you see f of 1 times 1. Okay, I have to be really careful because I need to be paying attention to what the function says to do to your x value. This says f of x is x squared, so for every single x value, I'm just going to square it. So down here, f of -1 is -1 squared. F of 0 is 0 squared. F of 1 is 1 squared. Okay, so when I do my final calculation and I add this together, I get that the approximate area, the approximate blue area would be 2. Right? It's not the best approximation, but it's better than nothing. All right? So let me point out that this notation is only used when you have a finite number of rectangles. So if you have 5 rectangles or 18 rectangles or 74 rectangles or 29 rectangles, okay? But what happens if you have an infinite number of rectangles? Now in that last video, I showed that the more rectangles you use, the better approximation you're going to get. So let me show you this, because if you have an infinite number of rectangles, that's what you see here, the notation changes slightly, right? Instead of having the sigma, you have what students typically call the s, right? It's an integral, right? It's still height times the base, right? So this looks different, delta x dx, right? Okay, still the base, still the height, still adding, but you are adding an infinite number of rectangles. So in this case, you should be getting the exact area under the curve, right? So you'll notice that now I can say where I started in my notation, start at A, end at B. Here I said start at -1, end at 2. This indicates I have an infinite number of rectangles to squeeze in there. And then if I'm going to be really specific, I can just say this is the antiderivative of x squared for this particular function from -1 to 2 dx. Now I want to try that in your calculator because your calculator can throw an infinite number of rectangles in there. You're going to have a hard time doing it, but the calculator will have no problem at all. All right, so what you're going to do is you're going to plug in y equals x squared. So you're always graphing the original function. Don't do anything to it. So x squared, graph that. And then you're gonna go second calc. Let me show you. What do I mean by second? This blue button, and then second from the right, second calc. And if you look at number 7, you can see there's that notation. It looks just like it, right? The integral of your function. So second calc, go to number 7. Your lower limit is going to be your a, so -1 in this case. And your upper limit is going to be your b, which is 2. And notice, look closely, it gives you the exact area under the curve. So it throws in an infinite number of rectangles between -1 and 2. Okay? So what do they say? If you throw in an infinite number of rectangles, you should get an antiderivative of 3. So this equals 3. All right, let me backtrack. When I use these 3 rectangles, notice I got an approximation of 2, which isn't bad. It's not too far off from 3. Right? So Riemann sums is, you're just trying to get an idea of what the exact area under the curve is. And so in my next video, we're going to talk about how to find the exact area under the curve using a process called the fundamental theorem of calculus.